So let's just go ahead and start off with your background. Maybe tell us a little bit about yourself.
Sure. So I was born in Lagos, Nigeria. Spent most of my sort of early years
Mm-hmm.
in Nigeria, which is a country in Africa. I moved to the U.S. first for my undergraduate degree at the New Jersey Institute of Technology. And I like to tell everyone I've sort of done a circle around the U.S. in my time here. So undergrad at New Jersey Institute of Technology, graduate school and PhD at University of Texas, which is South,
Mm-hmm.
and then came to Stanford for a postdoc
Mm-hmm.
on the West Coast, so East Coast, South, West Coast.
Mm-hmm.
Um, There, I was working at the intersection of AI and neuroimaging, neuroscience.
Mm-hmm.
I went to the Midwest, University of Illinois, Urbana-Champaign, for my
Mm-hmm.
first faculty position.
Mm-hmm.
And in the middle, I've spent a bit of time in industry. Spent mostly time at Google DeepMind in the
Mm-hmm.
middle in California, and now I've moved back to California.
Mm-hmm.
I spent time at Stanford University leading the Stanford Trustworthy AI Research Lab. We think
Mm-hmm.
around about trust and safety questions
Mm-hmm.
in AI, how to build better measurement tools and mitigation tools.
Mm-hmm.
And recently co-founded a company, Virtue AI, that is focused on enterprise-facing security safety questions. So they're building infrastructure and tools to help enterprises measure as well and mitigate security and safety problems. So tools around red teaming, guardrails, and other infrastructure, agent infrastructure as well that helps enterprises measure and mitigate safety and security issues in Gen AI for the enterprise.
Mm-hmm. Awesome. Maybe tell us a little bit about your time in undergrad and how you first got interested in computer science.
That's fascinating. So I just had a conversation 2 minutes ago. I have taken, I think, two computer science classes
Mm-hmm.
in my all of my education, which is
Mm-hmm.
not that unusual actually, but maybe awkward given that I'm a computer science professor.
Mm-hmm.
So almost all of my education was formally in electrical engineering.
Mm-hmm.
Um, and so I think one nice thing about electrical engineering is that it's either by design or consequence. It seems to be built such that people pick up lots of skills and can easily diverge in multiple directions. So, we spent a lot of time doing foundational math, particularly linear algebra, which actually served me really well once I got into machine learning, because so
Mm-hmm.
much of the machine learning foundations are linear algebra. In fact, I like to say that I started out actually quite a bit ahead of my pure CS colleagues when I
Mm-hmm.
got into the field, because all the sort of matrix algebra was standard for me because that's what we did in
Mm-hmm.
EE. And maybe people had to go from more discrete logic and sort of discrete math to more continuous math. And I think that was actually harder for many people. Of course, people are smart and people
Mm-hmm.
figured it out, but and I had a small advantage for a short time,
Mm-hmm.
having an EE background. I took programming classes as well. I think at the time I wasn't completely sure where I would go. For a
Mm-hmm.
lot of my career, I thought I would do sort of control systems
Mm-hmm.
adjacent kind of work. So the research I did in undergrad was with folks who were doing sort of control systems analysis kind of work, and
Mm-hmm.
I thought that's what I would do when I started grad school. And in fact, the first sort of set of professors I talked to were working broadly in control systems. So
Mm-hmm.
very similar math. Very close to things like reinforcement learning,
Mm-hmm.
actually. So, sort of lots of Bellman equation kinds of things.
Yep.
And so that was sort of where I initially started, even though I had some programming, because we do a fair amount of programming in E, like I said.
Mm-hmm.
However, I shifted actually. So I took a class on communication systems, physical layer communication. So this is the bottom level of the infrastructure that is how we build, particularly wireless communications. So this is sort of roughly the math and algorithms that allow devices to communicate with each other. And I got quite excited about that area and decided sometime early in my grad school to pivot. So I thought I would then be doing wireless communications.
Mm-hmm.
As part of my time there, I got interested in a project on software-defined radios,
Mm-hmm.
which was this idea to build intelligent wireless communication systems that would detect channel use, predict which channels might be empty. This is wireless channels, so
Mm-hmm.
bands, and
Mm-hmm.
then randomly swap to different channels,
Mm-hmm.
or not randomly, systematically swap to
Mm-hmm.
different channels based on availability. So it had a bit of, I think, early interesting sort of predictive machine learning in there.
Mm-hmm.
I like to say that I got much more interested in the machine learning part of this than the wireless part of this over time.
Mm-hmm.
So while I invested quite a bit in that direction, I did a couple of internships at wireless telecom companies.
Mm-hmm.
By the end, by sort of roughly around when my master's part of my PhD was over, I think I
Mm-hmm.
decided that I was more interested in thinking through algorithmic aspects of intelligence broadly, and so I got excited about machine learning and artificial intelligence.
Mm-hmm.
So started to do some work in that area.
Mm-hmm.
A lot of my PhD work was around probabilistic machine learning.
Mm-hmm.
So I spent a lot of time thinking through uncertainty, ways to do inference.
Mm-hmm.
At the time, this was circa early 2010s or before
Mm-hmm.
that.
Mm-hmm.
I think the locus, the sort of basin of attraction in the field where probabilistic inference methods and maybe support vector machines, I think
Mm-hmm.
that's where there was the most attention. So I
Mm-hmm.
spent a bunch of time thinking through. Some of the work was just better inference tools. At the time, each new paper would be like a new problem and finding a new inference method for that one problem,
Mm-hmm.
which I think has completely shifted. But at the
Mm-hmm.
time, this was the hard problem to solve in the field.
Mm-hmm.
My thesis was about trying to add constraints on the inference process, so control some of how we could get probabilistic models to fit and to work by
Mm-hmm.
adding various kinds of additional structure.
Mm-hmm.
And I did some of my application areas included collaboration with a neuroscientist colleague,
Mm-hmm.
which is how I got into sort of neuroscience. I liked it a lot because it was an area where I actually like the small data aspect of it, weirdly enough. So
Mm-hmm.
neuroscience and lots of scientific data has this property that there's a lot of data, but the
Mm-hmm.
data it's big in the wrong way, if you like. So huge images, say if you do brain scans,
Mm-hmm.
but not that many brain scans because brain scans are expensive. So you're gathering gigabytes of data per individual for only a few individuals,
Mm-hmm.
and in those kinds of areas, leaning strongly on scientific expertise to
Mm-hmm.
inform structure and build priors and things like that was an interesting, sort of exciting area to me. So I saw this as like using scientific expertise to inform how to build sort of probabilistic machine learning methods, and I spent a lot of time doing this. So I know I went a bit beyond your question, but you were asking about undergrad. I went all the way
Mm-hmm.
to grad school and maybe postdoc, but
Mm-hmm.
yeah, that's a bit of my journey on the scientific side.
Mm-hmm. Awesome. No, super duper duper helpful context. So maybe tell us a little bit about your time at University of Illinois Urbana-Champaign, along with maybe some of your time at DMind. I mean, you were at sort of DMind from 2018 to 2024. I think you were at UIUC from 2016 to 2021 as an assistant professor, and then now you're sort of an adjunct associate professor. Tell us a little bit about that journey going from University of Texas to becoming a professor, and then sort of like what motivated this decision to also get involved with DMind.
Yeah, great question. So I'll start with Illinois and then maybe
Sure.
expand from there. So at Illinois, I started my group initially mostly motivated by this foundation of structural priors for AI and ML systems. So
Mm-hmm.
I was thinking about this mostly sort of scientifically informed machine learning
Mm-hmm.
as the main place of focus. And I did a bunch of work with neuroscience colleagues.
Mm-hmm.
We studied ways to build better predictive models
Mm-hmm.
for sort of reading the brain, if you like. We
Mm-hmm.
build tools to help estimate connectivity, so how different areas of the brain connect to each other, and how that informs behavior, how that informs cognition.
Mm-hmm.
Fascinating area.
Mm-hmm.
Over time, my work expanded in a couple of different directions. So, one, I spent a bit of time
Mm-hmm.
on the application side beyond neuroimaging, and I took
Mm-hmm.
on almost serendipitously, but took on more things like healthcare applications.
Mm-hmm.
The story I like to tell, which I think is actually true,
Mm-hmm.
is that when I was at Illinois, um, from the outside looking in, so if people were looking for AI people that they,
Mm-hmm.
or machine learning and AI people that they might work with, who might be adjacent to human something.
Mm-hmm.
Uh, I looked close enough if you didn't know any better, even though I
Mm-hmm.
was doing mostly neuroscience work. And so I
Mm-hmm.
got a bunch of incoming and very interesting applied work around healthcare applications.
Mm-hmm.
And I ended up deciding this was interesting, investing some time in this, and ended up building, I think, both some research portfolio, but also investing some effort in healthcare has become one of my main applied areas.
Mm-hmm.
On the conceptual side, I think some of what shifted was going beyond generic structure and making that the foundation of thinking around uh, measurement questions and then trust and safety, trustworthiness questions.
Mm-hmm.
So the connection there is thinking of structure that comes from scientific expertise as sort of informing how to build robust machine learning tools for scientists who are looking to solve scientific problems and
Mm-hmm.
tools that they can use to make inferences for the kinds of problems that they're trying to solve. And in some ways that this expanded beyond sort of robustness and structure included spending a bit more time on other kinds of robustness and sort of robustness framings
Mm-hmm.
within the AI ecosystem. So I got into some work in things like causal inference and sort of other kinds of tools to build more robust models.
Mm-hmm.
I got into thinking around privacy primarily through I had a excellent collaborator, Indy Gupta at Illinois, and a great student, Simon Songxie, who, you know, it was a few years ago, so I moved on. And they got me excited around distributed machine learning. And one
Mm-hmm.
of the big motivations for distributed learning is decentralization enables more privacy. So you avoid having to get data all in one place. You can keep data where it's sort of collected and sourced. And the goal here is that this could minimize sort of some exposure to privacy issues. And
Mm-hmm.
beyond this, people do a bunch of work. We did work as well, strengthening the scaffold. So this typically the most popular of these approaches is called federated learning.
Mm-hmm.
But other ways of thinking about decentralized sort of training infrastructure,
Mm-hmm.
and you can further build scaffolds using other kinds of privacy tools. So I got into things like differential privacy
Mm-hmm.
and other kinds of ways of thinking around privacy specifically. So that covered some robustness, a bit of privacy, other aspects of trust and safety, and then maybe finally we ended up investing. Some of this started in my PhD work, but I think really came to a head early in my sort of first faculty position at Illinois, thinking around how we pick what we measure in machine learning methods and making that like a specific focus.
Mm-hmm.
So this came up because I'd spent a bunch of time on the probabilistic side trying to figure out how to build optimal learners. So the question is, if I give you some machine learning problem,
Mm-hmm.
I give you some exotic measure of goodness of fit or goodness of the result, right? So
Mm-hmm.
I give you, I'm measuring, say, a classifier, but the way that you're measuring this classifier is, some mix of the simple thing might be, I don't know, some weighted combination of how it is true positive and false negative behavior, but you could also have exotic things like some quadratic function of the statistics of the classifier over different subgroups or something like this. And I want to maximize this measure. And this is a sub problem of a larger set of problems where we're trying to solve machine learning problems for fairly bespoke measures of goodness or measures of correctness.
Mm-hmm.
And so I spent some effort on what are called Bayes optimal classifiers. So this is sort of understanding the probabilistic foundations of how to build good learners for complicated measures of correctness. And a lot of the feedback from that line of work when I was putting effort in it was that actually once you make clear that the results change depending on how you measured the problem, then the next question was like, how do I pick what to measure?
Mm-hmm.
And this is sort of this big open problem. And so this led our group to invest time on what we called metric elicitation. So this was effectively looks a bit like inverse reinforcement learning, but and sort of other aspects of sort of reward design and reinforcement learning and things like that. But these were focused on much more classic machine learning tasks, how to pick good evaluation measures based on human preferences. And some of this has come back when we come back to Stanford. I now teach a class actually on learning from human preferences, which is sort of building on some of these foundations. And so these roughly ended up expanding into now my broader frame around sort of trust and safety types of questions in AI systems. On DeepMind, very briefly, I initially got excited about DeepMind because they were, I mean, DeepMind is, well, at the time when I joined, it was called Google Brain.
Right.
Sorry, let me say this better. There was a DeepMind in the UK. There was a separate Google Brain around the world. Eventually, circa 2, 3 years ago, they got combined, as you might know, and many of your listeners might know. But I was working at Google through the sort of Google Brain part of it, which had this incredible sort of bottom-up research-oriented culture, and I think was actually a great place for me to learn and collaborate with some incredible scientists around. We actually did a lot of fairness work there, a bunch of work around causality, some work around aspects of improving training of things like language models and other kinds of systems. A bunch of interesting work around healthcare applications with other kinds of subgroups. I initially got interested because Google started a lab in Accra, Ghana, and this seemed an incredible opportunity to be sort of helping seed this new initiative in Africa, where there wasn't any sort of anything like that on the ground. So anything that was sort of research-oriented group on the African continent. And this seemed exciting. I was working with a colleague, Mustafa Sise, at the time, and so we ended up working with other great people to sort of start some of that initiative and start that group. So that was my time initially at DeepMind. Of course, this changed over time. I spent some more time full-time there, in transition between Illinois and Stanford. Some fun things there. I played a bit with some of the ad infrastructure, so tried to find some new methods to sort of improve some of the serving of ads, which is, I think, core to some of what Google does. Did other work around robustness and causality, some other healthcare work. I think it was a fun, interesting time. And since then, I've moved to Stanford, and as I already mentioned, leading a group thinking around trust and safety with a focus on measurement, evolving with some of the ways that the field has evolved and changed as well, and some of the company work as well.
Awesome. Yeah, thanks for the super duper comprehensive background. So sort of like leaping from this amazing background, let's get into some of your papers that are really exciting here. Maybe one of your most exciting papers, especially recently, is this titled paper called "Are Emergent Abilities of LLMs a Mirage?" Want to maybe just tell us a little bit about this?
Sure. It's been an interesting, somewhat controversial paper. It was one of the best paper awards at NeurIPS in 2023. The question that we asked in that paper is, to what extent are observations of what are called emergent abilities in language models a function of the designer or measuring the choices made by so the measurement process. And I think it was actually, for me, illustrative, in some ways, great example of how choices we make in measurement can have such an impact in what we see when we build algorithmic tools broadly. So the main thesis, if you're not familiar, so the phenomenon of emergence, it's a bit of a borrowed word. It's most popularly used in physics, but also has this colloquial definition. In physics, it mostly has a fairly clear technical definition on sort of complex systems and how you see phase transitions. Colloquially, I think people borrowed the phase transition language, but beyond that, it's quite a bit looser. So
Mm-hmm.
people, there's not a mechanism that's sort of well understood, but it's mostly an observation. The small models seem to be really bad at many things,
Mm-hmm.
and big models are quite a bit bigger at many things.
Mm-hmm.
And it seems that the transition between bad and good, between small models and big models, happens at different scales for different kinds of capabilities
Mm-hmm.
in a way that seems hard to predict. So the key thing that people seem to care the most about was the predictability aspect, which is, can we tell when a model will go from bad at something to good at something?
Mm-hmm.
So this animated resource allocation, if you're going to build resources and build in big AI systems, it animates a bunch of policy if you're worried
Mm-hmm.
about capabilities, but also safety and risk,
Mm-hmm.
because you want to understand how well you can predict sort of the next steps in the evolution of AI systems. I think a lot of this is also built around what are called scaling laws, which again are
Right.
predict how we understand how resource investments, typically data size, model size, training time, translates into error behaviors and performance behaviors in models.
Mm-hmm.
So the main result in the paper was looking at a couple of different existing work that had studied this phenomenon that had been called emergence,
Mm-hmm.
and mostly showing, on one hand, uh, that most of the observations of emergence could be better explained. Instead of having these explained as phase transitions in model behavior, they might be better explained as simply models, measurements using a sort of partial credit measurement versus non-partial credit measurement. So
Mm-hmm.
this is important because many of the applications where people had shown emergence were things like arithmetic
Mm-hmm.
type evaluation. So you're asking models to add numbers together, multiply numbers together, things like that.
Mm-hmm.
And what we mostly showed is that if you allowed for partial credit, so getting some of the numbers right, you saw a much more smooth, predictable curve. If you didn't allow for partial credit, and you were just checking everything correct or everything wrong, you saw what looked like, again, this sort of unpredictable shift in performance.
Mm-hmm.
We had a very simple, almost naive theoretical model that explained how you should expect compounding errors to lead to these kinds of phase transitions.
Mm-hmm.
And we showed that the theoretical model explained empirical observation quite well. So this again gave us further evidence that, again, it might be a measurement artifact more than anything very fundamental about AI systems.
Mm-hmm.
And finally, we looked at applications where no one had ever claimed emergence. So we looked at like computer vision applications, computer vision classifiers, and we changed the metric from the standard way people measure performance to something that didn't give partial credit. So we looked at things like autoencoders, which is a simple approach to sort of take an image and encode re-represent it in the latent space of some large AI model. And we showed that if I used partial credits, I got the standard results. If I used sort of 0, 1, I got what looked like emergence. This, again, we thought gave us stronger evidence that the measurement process had a big impact on interpretation. And I think has led to both some rethinking in the field about how to interpret epiphenomena that we're seeing in AI models. I think for my group, a lot of introspection around how we think about measurement and how measurement choices shape development of AI systems, safety and security issues. So it led to some investment in our work in this direction.
Mm-hmm. Awesome. Maybe another paper that you have that's really exciting is titled Leaderboard Illusion. You want to maybe tell us a little about this one?
Yeah. So this was a paper, I think, still under review, but we released this last year. This was a collaboration with a few other people, led out of Cohere, for AI, sort of their sort of research arm.
Mm.
And what they were interested in, so they had observed, I guess, that there seemed to be a meaningful gap between open source or some there seems to be a meaningful gap between, I guess, the quote unquote frontier AI model systems and
Mm.
the rest of the ecosystem. And, some of the gap could be explained by capability. Maybe the the foundation or the frontier folks are just building better systems. But they thought that there was more to say there. And I think this led to some scientific investigation on our end on what might be driving, what leads to leaderboards. What leads to some of the frontier models doing better on leaderboards versus other models?
Right.
It's worth saying briefly that this was done on Ella Marina. So Ella Marina is
Mm.
this ecosystem. It's become quite popular as sort of a way to measure and compare a bunch of AI systems with each other. The nice thing about Ella Marina is that it gets signals from people. So people can come in there, rate. You see pairs of model responses. You can rate which response you think is better or worse. And based on this signal, you can build rankings of models across sort of different providers. And so this is exciting because it allows for maybe a different signal than what you get from benchmarks. It's
Mm.
validation from sort of human preference
Mm.
at scale. And they've been quite successful, actually. And I think built a quite important, useful ecosystem for trying to understand how human preferences could help shape how to measure better or worse models.
Mm.
So help to rank models.
Mm.
And from there, they've done other things. I think the folks that built this have a company now and
Mm.
are doing things around this work. In the
Mm.
paper, we mostly critiqued what we saw as practices within the ecosystem that seem to systematically advantage some of the large providers that could put specific resources into what we interpreted as gaming the leaderboard.
Mm.
I think this is somewhat controversial and depends a lot on perspective. Like, what is it? What do you want from a leaderboard that claims to measure which models are better or worse?
Mm.
One perspective, which I think is where the Ella Marina folks are, is that what they're measuring and comparing are checkpoints that are submitted by the each any model that wants to get evaluated. So a
Mm.
model wants to get evaluated, to submit a checkpoint. They can submit as many checkpoints as they want. Every checkpoint gets evaluated, compared against each other, and at the end you get this ranking.
Mm.
However, when people interpret Ella Marina, they don't interpret multiple checkpoints. They interpret the entire model generation. So if
Mm.
I'm interpreting GPT 4.5 or Gemini current generation, I'm not interpreting Gemini, the 10 different checkpoints or 50 different checkpoints that were evaluated. I am interpreting its leaderboard position based on Gemini as a whole. So this leaves an interesting gap where, on one hand, the model providers can test lots of different models and see which ones do better or worse, use feedback from interaction with the ecosystem to try to improve their score. But are doing this at the micro model level. So they're not doing this for a single model, they're doing this for multiple sub checkpoints within the model.
Mm.
While on the other hand, the ecosystem is interpreting the results based on entire model generation. So,
Mm.
here's a newly released model. What was its ranking on Ella Marina?
Mm.
As opposed to, here was the ranking of this particular checkpoint and how did all the rest of the checkpoints do compared to this checkpoint? And so what this paper tried to argue was that this sort of checkpoint process, we think, creates a gap between the interpretation from the ecosystem and what the providers, and honestly what Ella Marina is intending to do. So again, Ella Marina folks, awesome. They have they're very clear on what they're intending to do, and they're doing exactly what they said. However, the interpretation from the ecosystem is very different from what they intended, which allows for this gap that we interpret as gameability, because it means that the public interpretation of sort of what model is better or worse is influenced by this ability to do a little bit of extra model fine tuning, play with which models you actually end up picking and releasing. The most public and version of where this led to some maybe public issues is maybe Llama 4, where the model that they used for Ella Marina to get high in the rankings was very different from the model they released elsewhere,
Yeah.
because they knew that Ella Marina rankers tend to like fairly syncopatic type of behaviors, and so they gamed for high sycophancy and did really well on Ella Marina rankings,
Mm-hmm.
but not for, again, the generation, but for a particular checkpoint that they knew would do well there. And then they released something else. And I think people noticed more than any other model the gap between the thing on El Marina and the thing broader in the world.
Mm-hmm.
So, I mean, the particular example I think is interesting as a narrative, but I think it again points to this bigger picture of measurement processes, incentives within the ecosystem,
Mm-hmm.
interpretations of measurement, which I think is the more salient point. Measurement is not abstract. It drives behavior, it drives prioritization, and it matters what you think you're seeing when you're
Mm-hmm.
interpreting some number or some ranking.
Mm-hmm.
And there's a mismatch that can happen, and this mismatch can lead to gamification. And if that's not what you want, and it may be okay, but if it's not what you want, which is the argument in the paper, then there's space to try to robustify measurement processes against these kinds of potential gamification.
Mm-hmm. Awesome. Another paper that's really exciting, how do large language monkeys get their power laws? Maybe just tell us a little bit about this one, and then we can get into some of your work with Virtue.
Sure. So that paper was built on an observation. So both that paper and also, by the way, the earlier paper we discussed
Mm-hmm.
was led by students Ryland Schaefer and
Mm-hmm.
some other folks in the group. So just lots of credit for, I think, his ingenuity in thinking, helping define some of these
Mm-hmm.
directions.
Mm-hmm.
The this paper on power laws came from a couple of observations that we'd seen
Mm-hmm.
on papers that had done test time compute in the ecosystem.
Mm-hmm.
So there are many ways to do this, but as you might know, some of the paradigm shifting that has happened in the field has been this move from mostly thinking around resource investment and pre-training. So how do I make models better as they get, say, bigger or use more data?
Mm-hmm.
To, can I do some things at test time?
Mm-hmm.
So can I, spend more efforts, say, calling models several times and having some kind of judge, or doing some kind of RL-based reasoning, combining different results, and is that a path towards improving model performance?
Mm-hmm.
And so we had seen this in a variety of different work with Ron and some other people at Anthropic. We had written some papers on best event jailbreaking, so this is on the security side, where we had seen that if you repeated even very simple jailbreaks multiple times, so this is a kind of test time compute, but this is on adversarial sort of attack side of things, you see what looks like very classic scaling law, power law kinds of behavior as you increase sort of the amount of tries that you have. So this is maybe the simplest way that you could do test time compute, which is just repeat a bunch of times and check how many times you solved the answer correctly. This works well if you have some verifier that tells you when you have correct answers. This works well for math and some of the other areas that look like this. With another colleague here at Stanford, Azalea, she had been using the same kind of techniques for trying to build sort of AI code kernel, like ways to improve kernel code design using, again, this repeated sampling kind of idea. And she had written a paper titled Large Language Monkeys, which is tied to this sort of classic, it is, I forget who it is attributed to, but this framing that says, if I allow monkeys to type randomly, informally, I'm paraphrasing because I don't remember the exact saying, but the rough saying is if I have monkeys type for infinity amount of time, they'll eventually produce Shakespeare because in infinite random words, there's going to be randomness is such that there'll be a random subset of strings that if you allow for infinity, all of Shakespeare must be contained somewhere in the random set of strings as a probabilistic conceptual argument. So they played with this analogy. They'd written this paper. For them as well, they ended up seeing this parallel kind of behavior, very classic scaling law. And for this paper, actually, there was a bit of a conundrum because we were seeing over and over again that repeated sampling
Mm-hmm.
is giving you power law type of behavior, experimental performance. So where the x-axis here is like log how many times are you trying, and the y-axis is some performance measure.
Mm-hmm.
But actually, if you look at the theory, a theory being like, what should you expect if I have some coin flip, some probabilistic model that
Mm-hmm.
I'm trying over and over again? How quickly should I expect it to improve? It actually improves much, much faster, actually. So there's this sort of geometric argument that comes from very basic probability. In fact, a colleague of mine, Chris Peach, assigned this question as a homework question in like a freshman, first year or second year Stanford undergrad class because it's actually quite intuitive. What you should expect if I flip a coin many times. It's also tied to the emergence paper. But if I flip a coin many times, how quickly should I expect to get a one, right? If it's a correct result. And it turns out that you should see ones much more quickly than we're seeing in parallel behavior. So
Mm-hmm.
somehow theory says we should converge faster. In practice, we're converging actually slower than we expect to be seeing. And so there was this gap. And so what the paper shows is that the reason that we have this gap is because not all problems are similarly difficult. So some problems are harder, some problems are easier. One way to operationalize difficulty is how easy, what's the probability of success when I repeat a certain problem over and over again. Some problems
Mm-hmm.
have a higher probability of success. So they start off, just throw a number, 0.25. And so I'm more likely to get a success after a certain number of tries. Another problem might be 0.002.
Mm-hmm.
And so it'll take me a long time of coin flips before I see a one if it has a 0.002 for a heads tail probability.
Mm-hmm.
And so we ended up showing that one, you actually need, so it's an if and only if theoretical claim.
Mm-hmm.
If you have a certain distribution of difficulty, you see a power law as the average aggregate performance over a bunch of different questions, say in a benchmark or in some kind of a coding test tool. And the other way is also true. You can only see power law behavior if you have a certain kind of distribution of difficulty. So it turns out that understanding, this is one of the lessons we took from it, understanding aggregate behavior can be done much more accurately if you understand behaviors like sub-aggregated, so individual, say, questions, individual models, like understanding what's happening under the hood when we do aggregate measurements can actually inform quite a bit on what we're seeing when we're seeing sort of overall averages, things like power law as an average behavior of a model family over, say, in this case, over repeated sampling, but you can also do this over other kinds of interventions. And now we're investing in this direction, actually, trying to understand to what extent can we build better tools to understand sort of individual at a sort of sub aggregate level. So looking at more fine grained steps in how we build measurement tools. Can we understand those better to then make better predictions about aggregate level behavior? And so there's some theory there. There's a bunch of practical results there. We have better prediction of scaling behavior because we now better understand what's driving test time scaling using repeated observations. Again, the distribution of difficulty being a sort of key underlying factor.
Mm-hmm. Awesome. And getting into our last paper here, and also starting to get into some of your work with Virtue, you had a paper titled Decoding Trust, a Comprehensive Assessment of Trustworthiness in GPT Models. I think this was co-authored with Don Song and Bo Lee as well. And I think Bo is also part of Virtue. So maybe just tell us a little bit about how you ended up joining this paper, the general effort at a high level, and then
Yeah.
what motivated you to join Virtue.
Yeah, yeah. So lots of credit to Bo for this paper. This is sort of her brainchild. She was working with some folks. Started off with some folks at Microsoft, and so they're also on the paper, and eventually expanded. So with other colleagues, and eventually at some point, myself and a few of my students helped contribute to this paper as well. At the time, there was no work looking holistically around trust and safety evaluation of language models. There's a bunch of work on capability evaluation, notably, for instance, work by my colleague Percy Liang on Helm, which is holistic evaluation of language models, and a bunch of other kinds of leaderboard tooling around this question, but very little on the sort of trust and safety side. And so I think at the time was notable for being the first paper that tried for holistic evaluation of trust and safety of models. We looked at a variety of different perspectives and a taxonomy across potential failure modes of language models, all the way from things like toxicity to adversarial
Mm-hmm.
robustness to
Mm-hmm.
privacy issues,
Mm-hmm.
and built tooling, so evaluation processes, so tests
Mm-hmm.
for how well models might perform
Mm-hmm.
with respect to trust and safety questions.
Mm-hmm.
And so the main results of the paper, I think the most interesting result of the paper is that actually for some risks that we evaluated, uh, more recent models actually tended to do worse. So for most risks, models were getting better over generations,
Mm-hmm.
which is maybe not surprising because there's some effort built into trust and safety. People are
Mm-hmm.
care about some aspects of model behavior,
Mm-hmm.
and so generally those things have gotten better. But what we notice is also one other thing that had gotten better is instruction following in models.
Right.
So models are just better at doing the thing that you tell them to do.
Yep.
And it turns out that instruction following creates a vulnerability for certain parts of trust and safety.
Mm-hmm.
It's in fact how a lot of jailbreaking and sort
Mm-hmm.
of prompt injection works.
Mm-hmm.
And in that paper, we mostly showed that, particularly for some of the adversarial attack kinds of settings, you could exploit the fact that models are better at instruction following to actually make them do worse on some of the trust and safety evaluations,
Mm-hmm.
where older models that would just not follow the instructions as well would have
Mm-hmm.
ended up doing better. So I think that was a once said, maybe not surprising, but I
Mm-hmm.
think at the time for us a little bit of surprising finding.
Mm-hmm.
The paper got some, I think, interesting buy-in in the community.
Mm-hmm.
It also won a Best Paper award in the same year on the data sets and benchmarks track of
Mm-hmm.
NeurIPS.
Mm-hmm.
And has, there's a Hugging Face leaderboard, a
Mm-hmm.
bunch of different downloads, part of Helm as well. So
Mm-hmm.
I think has given us some interesting platform to think around measurements of trust and safety questions
Mm-hmm.
and AI systems. I'd say, you know, so some of the paper was part of the nexus of thinking around, hey, there seems to be a gap in industry
Mm-hmm.
here around deep understanding of evaluating AI system capabilities,
Mm-hmm.
using state-of-the-art research tools,
Mm-hmm.
and coming up with methods that can help us mitigate some of these questions. And we didn't see anything out in the sort of enterprise space, and we thought we could, say something meaningful here. And so starting to talk to potential customers, starting to talk to each other, and eventually this led to helping co-found Virtue AI, where Bo Lee serves as CEO, and a bunch of us. So the co-founders, Bo Lee, Don Song, and Carlos Gestrin, and myself.
Mm-hmm.
And it's been a couple of years, maybe a year and change
Mm-hmm.
actually. The company has grown reasonably quickly. We've been fortunate to work with lots of, I think, great enterprise customers. So we
Mm-hmm.
work with all the foundation model companies,
Mm-hmm.
helping out with evaluation. We work with a bunch of enterprises,
Mm-hmm.
helping them with both evaluation, so things like red teaming, but also with mitigation issues. So we help them build guardrails and other
Mm-hmm.
kinds of software tooling around security and safety questions. And so I think, many things interesting. The shift or the gap between academic questions on safety and security and the enterprise facing ones, I think, has been fascinating. So what do enterprises actually care about, and how do you build tooling that helps them engage with this problem? Some of the governance questions that look different from the academic view, and even policy view, because I've gotten into some policy
Mm-hmm.
and governance and how that looks differently from the enterprise point of view.
Mm-hmm.
Thinking through, some of this is just nuts and bolts, things like sales and marketing, but also things like infrastructure, right? So
Right.
your tooling has to scale well in the enterprise context. And
Mm-hmm.
so a bunch of there's the model building, which is
Mm-hmm.
in some ways familiar to academia, but then
Right.
there's this sort of scalable infrastructure components of this if you're going to deploy in an enterprise setting that looks quite different than what at least I am used to.
Yes.
I have colleagues who work in systems who are much more familiar with this part of the work, but typically I'm thinking I stop at the model because that's typically what I'm most excited about. So that's been incredible learning and thinking through how to solve these problems at enterprise scale and working with some enterprise partners across different verticals. Excited recently to start to invest on. So a lot of our early customers were on the sort of general enterprise services side, so
Mm-hmm.
folks like Uber and folks
Mm-hmm.
like that. Very recently, we started to invest in finance as
Mm-hmm.
an interesting vertical
Right.
where there's a lot of adoption and deployment of AI tooling and
Mm-hmm.
a meaningful and important gap, partially because of regulatory pressure
Mm-hmm.
and partially because just finance is a more conservative
Yep.
sort of vertical,
Mm-hmm.
thinking through how you can solve sort of security and compliance and safety issues
Mm-hmm.
for them. And so recently signed on AB as a customer, working with a bunch of other enterprise customers in finance space.
Mm-hmm.
So, learning a ton around trust, safety, compliance, and
Mm-hmm.
AI systems in finance, but more broadly in enterprise. And I think
Mm-hmm.
it's been a sort of quite fascinating, interesting experience so far.
Awesome. So as we get very, very close to the end of time here, our very last question, like what are some areas that you're very, very excited about these days? I mean, obviously we sort of hit like five different papers that you worked on. You're obviously working on really great stuff through Virtue. You have an amazing lab, like we talked about earlier. And so there's so many different areas. There's been like a lot of people talking about like RL environments, scaling RL. There's, a lot of different startups that are doing interesting things in those areas. What are some sort of emerging categories that you're excited about from a research perspective, and then also from like an enterprise product perspective?
Yeah. So maybe I'll start with the enterprise product because I think maybe more straightforward. So I
Yeah.
think um, investing in where enterprises are now, which a
Yeah.
lot of is mostly around chatbot kinds of use cases for
Mm-hmm.
Gen AI systems. I didn't mention this, but worth mentioning. While a lot of the focus is on text, we also virtualize multimodal. So we
Right.
work with companies who are doing voice, audio, video, code as well.
Mm-hmm.
So I think that whole part of the ecosystem is also very interesting, particularly code use.
Mm-hmm.
So it turns out vibe coded software has lots of security gaps,
Yep.
maybe not surprising.
Yeah.
And so helping solve some of these issues, I think, has become an interesting new focus for us. I think the most exciting frontier is within companies, there's a shift towards giving AI models more agency. So this is
Mm-hmm.
colloquially called AI agents.
Mm-hmm.
AI agents mean many different things to different enterprises,
Yeah.
but the core is that you're going from sort of computational systems that have humans very closely tied in
Mm-hmm.
implementation of say the usage and loop of
Mm-hmm.
these systems. So things like chatbots, things like summarization, where a human is ingesting the information as the
Mm-hmm.
primary target, to now settings where humans are may potentially not in the loop, right?
Mm-hmm.
So the AI systems are taking actions, answering your
Mm-hmm.
email,
Mm-hmm.
booking tickets, all that kind of stuff.
Mm-hmm.
And so the risk surface grows actually, maybe not surprising, but
Yeah.
now you have not just prompts and responses, but now you have actions that agents can take, network traffic, reasoning processes,
Mm-hmm.
whatever it is the planner does, the MCP infrastructure itself. And so a lot more risk surface, a lot more spaces where things could potentially go wrong. And so we've been spending some effort in beefing up our product offering to
Mm-hmm.
engage meaningfully in the sort of agentic safety and security
Sure.
and compliance space. And so building some tooling to help solve those kinds of problems. On the research side, so my group is very excited uh, around how measurements foundations can help us understand trust and safety questions broadly defined. So, roughly, we have three broad areas. So, we invest in what we call measurement science. So, this is like thinking about broad frameworks around better AI measurements, thinking about predictability and AI evaluation. Some of this looks like things like scaling laws, the two papers we talked around
Mm-hmm.
about where, scaling laws in different kinds of contexts. So
Mm-hmm.
can we build better tooling, infrastructure, methods? Some of this looks like software tooling. Some of this looks like foundational sort of modeling approaches to better
Mm-hmm.
understand predictability and measurement processes. We spend a lot of time thinking around things like validity. So how do
Mm-hmm.
we make sure that the measurements capture what we actually care about
Mm-hmm.
in AI systems? We're learning from areas like there's a well-developed measurement science in
Mm-hmm.
places like education and psychology and other fields. So learning from those sort of foundations.
Mm-hmm.
Second aspect is trust, where the AI in society. So there we think around things like fairness, privacy,
Mm-hmm.
things like alignment, learning from human
Mm-hmm.
preferences. So we've done some work in unlearning. I think that's maybe we spent a lot of effort there.
Mm-hmm.
Tied to privacy, how can you remove information from AI
Mm-hmm.
systems? Recently published at ICML, to our knowledge, the first method that can provably enable learning for sort of deep learning kinds of models.
Mm-hmm.
We had a ACL best paper on contextual fairness kinds of settings and how to
Mm-hmm.
evaluate them. So spending some time investing in that direction. And then
Mm-hmm.
third, AI applications and real world impact. So
Mm-hmm.
we think around healthcare, I talked about briefly,
Mm-hmm.
but also policy, other kinds of industry applications, scientific applications. So we're looking to sort of bridge rigorous science with practical societal needs.
Mm-hmm.
And our goal is to be a meaningful component of how to build AI systems that are worthy of trust that society will end up placing in it. So we want to be able to measure and understand where gaps might show up,
Mm-hmm.
build tooling that helps mitigate those kinds of gaps all the way up and down the stack.
Mm-hmm. Awesome. And without further ado, thank you so much for coming on the podcast.
Yeah, it was a fun chat. Thank you for the questions.